This is Jack Jackson, and we're going to continue in this video to be talking about the sum rule for derivatives. So in our last video, we saw that the derivative of f of x plus g of x is f prime of x plus g prime of x. So the derivative of the sum is the sum of the derivatives. Now we proved that. I'll go over the proof again real fast. The derivative of the sum is the limit as h goes to 0, that sum of x plus h minus the sum of x over h. Well, that sum function of x is just f of x plus g of x. And when you evaluate that at x plus h, you evaluate f at x plus h and g at x plus h and add them together. Now, we're going to distribute this subtraction here, which we do there, regroup by putting the f's together and the g's together, use the distributive property to break this into two fractions, which we've done here, and then make our limit property of limits says breaks this into two limits. The first limit is the derivative of f, the second limit is the derivative of g. So that proves that, but we can generalize this rule to sums of even more functions here. We can have the derivative of a sum of n functions together. Now let me get this where I want it. So if you're taking the derivative of a sum of n functions, you just get the derivative of each one and add it together. And the proof is pretty easy. It's just a repeated application of the same thing. So for example, if you had the derivative of three things, you'd group two together and say it's the derivative of two parts, which is the derivative of the third one plus the derivative of the sum of the first two, and apply the rule over and over again. Formally, to do this proof, we'll do this by what's called mathematical induction. So the basis step is trivial for n equals 1. The derivative of one function is the derivative of that function. And the sum rule that we have up here already proves that it works for n equals 2. So the way the induction step says, let's suppose this is true for n equals some number m, and then let n equal m plus 1. So we want to sum up those n functions and take the derivative. Well, that's the sum of m plus 1 functions. Group the first m together, and then you got the m plus 1. Now you have this derivative of two things. This first one's a big sum, and then the last one. According to the sum rule for derivatives of just two functions, sum of two functions, you get the derivative of the first one plus the derivative of the second. According to our induction hypothesis, this first part is the derivative of each part added up together. And of course, that's just the derivative of all n things added together. And so by the principle of mathematical induction, the result is true for all natural number values of n. So this allows us to take the derivative of any function whose outermost structure is basically a sum of other things, or at least it allows us to take that and to break it down into a bunch of smaller derivative problems added together. Hopefully each one of those smaller things is something we might know how to do. For example, we already know how to do derivatives of power functions. So the derivative of x to the fifth plus x to the third is the derivative of x to the fifth plus the derivative of x to the third. That one's 5x to the fourth. That's 3x squared, and we add those together. Okay, so you see if you can do that and apply it to this problem here. Now, what that is going to be is just the derivative of each part. So this is going to be the derivative of x cubed, which is 3x squared, the derivative of the x, which is 1, and the derivative of negative 5, which is 0, which is 3x squared plus 1. And actually, this is easy enough. You can do the whole thing in your head, right? Just 3 times the 1, the power goes down 1. 1 times 1, power goes down to 0, so that term goes away. The x part goes away. This constant term, the derivative goes away altogether. Okay, here's a contextual application. Galactic Robot sells two models of robots, the C3 and R2 series. Income from the C3 series has been increasing by $500 per year, whereas the income from R2 series has been decreasing by $200 per year. What's the rate of change in the revenue from the sales of the robots? Well, if T is the total revenue, C is the revenue from the C3 series, and R is the revenue from the R2 series, and T is time, we see that the total revenue is T of little t is C of t plus R of t, and by the sum rule, that's T prime equals C prime plus R prime, and we're given C prime and R prime. C prime is 5,000, R prime is negative 200. So that means they're gaining $4,800 a year. So the total revenue from sales is increasing by $4,800 per year. In economics, we usually let R be the revenue. So maybe this is a poor choice of R up here, or poor choice of C up here because it's the cost. So C is the cost and R is the revenue. Now, and P is the profit. These things are taken from the producer's standpoint. So the R is the revenue, is the total amount of money brought in by the producer, and C is the cost, is the amount of money it costs the producer to provide its goods or services, to make them and market them. So that it's not the cost to the consumer, it's the cost of the producer. And the profit is revenue minus cost. So revenue, cost, and profit can be thought to be functions of the quantity, let's say X, of items made. We take the word marginal to mean derivative. In formula form, write down the relationship among the profit, cost, revenue, and marginal cost, marginal profit, marginal revenue. What relationship do we have there? And what's the meaning of the marginal relationships in economic terms? And what does this say about maximizing profit? If you need to, pause and think about that a minute before you move on. Well, profit is revenue minus cost, so P of X equals R of X minus C of X. Marginal profit then is marginal revenue minus marginal cost, that is P prime of X equals R prime of X minus C prime of X. The marginal relationships indicate that the amount of additional profit from making one more item is the additional revenue from that item minus additional cost of making that one item. And profit is maximized when the derivative is 0, P prime is 0, which is when R prime equals C prime. In other words, the profit is at a maximum, or could also be at a minimum, when the marginal revenue equals the marginal cost. That is, when the amount it costs to make one more item is equal to the revenue generated by selling that one more item.